We are going to explore the mysteries of classical correlation and quantum entanglement, see the similarities and the big intrinsic differences. Imagine two objects connected in some way. In the world we experience, these connections often follow predictable rules. But when we delve into the quantum realm, things get much stranger. Let's start with something we can all understand, the classical correlation. Think of a rocket launching into space. When it explodes, the two pieces fly off in opposite directions. This is because of the conservation of momentum. The total momentum before and after the explosion must be the same. This is a classical correlation. It's a direct result of the laws of physics, and it's entirely local. The two pieces are connected by a causal relationship. One event causes the other. Quantum entanglement is a much more mysterious phenomenon. Imagine two particles that are created together in a special way. They become linked or entangled so that no matter how far apart they are, their properties are correlated. If you measure one particle to be spin up, the other will instantly be spin down, no matter the distance between them. In the case of entanglement, the state of a particle is not defined until it is measured. The measurement on one particle instantaneously alters the state of the other, even across a distance. Entanglement is not merely the result of a conservation law. It is an intrinsic correlation between the quantum states of particles that cannot be explained by local or predefined variables. Entanglement is described by a shared quantum state, represented by an overall wave function. This state does not allow each particle to be described independently. This instantaneous correlation is what makes entanglement so strange. It seems to violate the speed of light limit, as if information is traveling faster than light. But this is not the case. Quantum mechanics simply doesn't obey the same rules as classical physics. Before to go further, if you like science contents, do not forget to subscribe, like, and start the conversation in comments. Let's summarize the key differences between classical correlation and quantum entanglement. Classical correlations arise from conservation laws, while quantum entanglement is a fundamentally quantum phenomenon. In classical systems, measurement doesn't change the underlying state. In quantum systems, measurement can collapse the wave function and change the state of the entangled particles. Classical correlations can be described using classical variables, while quantum entanglement requires the language of quantum mechanics and wave functions. Quantum entanglement exhibits non-locality, meaning that measurements on one particle can instantly affect the other, regardless of distance, while classical correlations are always local. One of the most profound ways to distinguish between classical and quantum correlations is through Bell's inequalities. These are mathematical inequalities that any theory based on local hidden variables must obey. However, experiments have shown that quantum entanglement violates these inequalities, confirming that quantum mechanics is fundamentally non-local. Imagine a debate between the giants of physics. On one side, Albert Einstein, champion of local realism, believing that everything in the universe must obey the rules of cause and effect, with no spooky action at a distance. On the other side, the predictions of quantum mechanics suggesting a deeper, more interconnected reality. This debate, fueled by Einstein's famous quote, "God does not play dice with the universe," led to a profound question. Can we experimentally prove whether quantum mechanics truly defies our classical understanding of reality? Enter John Bell, a physicist who, in the 1960s, devised a brilliant test. He derived a set of mathematical inequalities, now known as Bell's inequalities, that must be obeyed by any theory based on local hidden variables. Essentially, any theory where the properties of particles are predetermined and local interactions are the only way they can influence each other. The idea is simple, yet profound. We create pairs of entangled particles like photons and send them to distant detectors. At each detector, we randomly choose a measurement setting and measure a property of the photon, such as its polarization. By comparing the results of many measurements, we can determine whether the correlations between the measurements obey Bell's inequalities. But performing these experiments is incredibly challenging. There are two main loopholes that can undermine the results. Not all particles are detected in the experiment. This can lead to a biased sample and potentially mask a violation of Bell's inequalities. If there is any possibility of communication between the detectors, even at speeds slower than light, It could explain the observed correlations without resorting to non-locality. Today, state-of-the-art experiments have successfully closed both loopholes, demonstrating a clear violation of Bell's inequalities, and Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize for their studies on quantum entanglement. These experiments provide strong evidence that the quantum world is fundamentally non-local, that entanglement is a real phenomenon, and that our classical intuitions about reality need to be revised. If our background world is intrinsically non-local, is there any way to reconcile our intuition with a consistent theory that takes into account quantum phenomena and a coherent description of the universe? In a further video, I will explore few possibilities that have arisen recently and can be rules changer. Follow us, like, and join the conversation in the comments for more. Quantum entanglement is a truly bizarre phenomenon that challenges our understanding of reality. It's a testament to the power of quantum mechanics and opens up a world of possibilities for new technologies, from quantum computing to secure communication. While classical correlations are based on familiar principles, quantum entanglement reveals a deeper level of reality, where particles can be connected in ways that defy our intuition.